Knowing the definition of a group now allows us to look at other mathematical environments safely. And what we want to do today is find some universal properties inherited by all group structures. Let's get started. You may have seen examples of groups where we have addition as an operation or multiplication as an operation. They have different identities, different types of inverses. But now what we're allowed to do with the definition of the group is make statements about all groups. And so, for example, we want to know if I have an identity element in a group, is it possible to come up with an example of a group where I have two identity elements? And the answer to that is no. So how do we prove that the identity element in a group is unique? Typically, the way to show uniqueness is to assume that it's not unique and either derive a contradiction or to show that those two elements actually were the same thing in the beginning. So we're going to start off with two identity elements. Now, by the nature of an identity, if I multiply anything by the identity, I get the identity. So since E1 is an identity element, if I say E1 star E2, that's the same thing as E2 star E1. It gives me the identity element E1. But also, I could go the opposite direction. E2 star E1 equals E1 star E2, which is E2. So by the transitive property of equals, this implies that E1 actually was E2. So there we have that identity elements in the group have to be unique. All right, let's look at another exercise. This time we have two things in our group A and B, and we multiply them together. And what we want to know is what is the inverse element of that multiplication product, that AB element. And can we relate it back to A and B itself? And the truth is we can. So if AB are elements in a group, then AB quantity inverse is B inverse times A inverse. Now how would we prove that? We need to use the fact that we're looking at inverse elements. So first I know that if I multiply AB by the inverse of AB, then just by definition of inverses, that is going to be my identity element. Similarly, if I multiply AB by B inverse A inverse, I believe I'll also get the identity element. And this highlights why the associative property is so important in the group definition. Because I can rewrite AB times B inverse A inverse as A times B inverse times A inverse. And we know B times B inverse is the identity element. So AE A inverse is just the same as A times A inverse, which we also know, again, is the identity element. So there we have it. We multiplied AB times the definition of AB inverse and got the identity. And then we multiplied AB times B inverse A inverse and got the identity. So those two things that we multiplied AB by must be equivalent. And that's the end of our proof. Now, sometimes these questions are difficult for students because we are trying to somehow directly equate AB inverse to B inverse A inverse. We don't know if we can distribute that -1 exponent the way that we are familiar with. I mean, that's exactly what we're trying to prove. So what we have to do then is go back to what the definition of AB inverse means. It means the inverse element of AB. And we show that both sides of these equations actually serve as inverses of AB, thus they have to be equivalent. I hope that makes sense, and I hope also you see how important the definition of the group is. Let's look at another one. All right, this time we say if G is a group and we have three elements, A, B, C, and G, then BA equals CA implies that B equals C, and AB equals AC implies B equals C. So this is what we would call our cancellation laws. And if we're trying to solve equations in these group environments, we would like to be able to say if BA equals CA, then that implies B equals C. All right, so let's take a look at this. So first, let's let BA equal CA. Now, an important part of the group is that we have an A inverse. So what I'm going to do is multiply both sides of this equation. On the appropriate side, here on the right side, I'm going to multiply both sides of this equation on the right side by A inverse. And keep in mind, when I say multiplication, I mean whatever the respective operation of the group is. That's just usually what we say. Now we apply the associative property. We group A and A inverse together on each side of the equation. And that gives us then that B equals CE. And we understand that that means that B must be C. We could do the exact same thing on the left side. So we call this the right cancellation law. The left cancellation law works exactly the same. I just have to rewrite my question. And so we easily showed cancellation laws. Now you've been doing cancellation laws your whole life. When I have an equation like 2x plus 1 equals 0, the first thing that you want to do is to bring the 1 over to the other side, right? We subtract 1 from both sides. What I'm actually doing there, though, is not just subtracting 1. I am adding in the additive inverse of 1 to both sides. And so that's how we get 2x equals negative 1. From there, to get rid of the 2, I am multiplying by the inverse of 2 on both sides. And so that's why we get x equals negative 1 halves in this particular question. And that's because the real numbers have both additive and multiplicative identities. That structure is called a field that you'll encounter later on in your algebra journey. All right, so let's look at this theorem. We have for two elements g and h in G, that g to the m, g to the n is the same as adding those exponents together, g of n plus n. So these are our exponent laws, and they look very familiar to us, at least the first two. Multiplying two things together means you add their exponents together. Raising exponents to a power means you multiply the exponents together. This third one's kind of unusual. Gh to the n power it's flipped around, h inverse g inverse to the negative n power. But if it's an abelian group, meaning that we have commutative operations, then you can just distribute the nth power just like we'd hoped. All right, let's prove this. So the proof for 1 is actually pretty easy. When I say g to the m, what I mean by that is g times g times g, a total of m times. So if I have gm times gn, and this is maybe a little bit more of a sketch than a formal proof, but I'm writing g times g times g m times, and then I'm writing g times g times g n times. So if I drop my parentheses or drop the association, then I have g times g, a total of m plus n times. There we go. There's our first one. For our second statement, we have g to the m raised to the n. Well, that's gm n times. And one way I could think of that is maybe writing each one of these as g times g times g m times. And so how many g's do I have in total, all being multiplied together? I have m times n g's being multiplied together. So that's g to the mn power. Okay, now those are both kind of just sketches. Okay, for this third part, what we're wanting to say is, well, how do we distribute the nth power? And we have this weird expression, h inverse g inverse to the negative n power. And one thing we need to know about notation here is if I write a to the negative power, negative n, that means either a n inverse or a inverse to the n power. All right, so I think what we want to do then is to rewrite this h inverse g inverse to the negative n as h inverse g inverse inverse all to the n power. And so what we mean by that then is that we're writing h inverse g inverse inverse multiplied by itself n times. Okay, now remember our last theorem said that the inverse element of AB is B inverse H inverse, right? So that means then that the inverse element of H inverse G inverse, which is exactly what I have here, could be written as G inverse inverse, which is G, times H. And then the next one is going to be G inverse inverse times H inverse inverse. And then the next one is the same thing. And we do this together, this time n times. So in totality, we have GH to the nth power. Now, if this is an abelian group, then I can take this expression and just rearrange my terms to get G to the n, H to the n. So there we have this weird expression for GH to the nth power. Hopefully we're an abelian group. It makes our work a lot easier, right? Okay, so we went over a few properties of groups, and this is true for any group. So any environment with any operation, as long as it satisfies the group properties, we have these things. So now that we know a little bit more about group structure in general. I hope this makes sense. If you have questions, you can let me know. Leave a comment, send me an email. Just keep looking at it. It's a new thing, but you just got to keep practicing. I look forward to seeing you next time. Thanks for watching.